right, so we're starting a unit on polynomials. We're going to kind of ease into things a little bit. So today we're going to talk about monomials. Mono means one, poly means many. Monomial just means one term. Polynomial, which we're going to talk about, would be many terms. A polynomial is a sum of monomials. So we'll just start with a monomial though. So a monomial, if you look at the anatomy of a monomial, this is it. A monomial contains a coefficient. It's got two parts, a coefficient and usually, but not always, a power of one or more variables. Okay, although a monomial may also just be a number, numerical constant. So the coefficient part, that's the number in front, right? We know what coefficients are. The coefficient must be a real number. And in the power part, if there's a power in the polynomial, the exponents in the powers must be whole numbers. So they have to be 0, 1, 2, 3, 4, etc. They can't be negative, can't be fractions, can't be decimals, has to be a whole number. So here are some examples of monomials. Pi, that's a monomial. It's just a number, right? A positive constant, or it doesn't have to even be positive, just a real number constant. 2x cubed. There's a monomial. Did you finish up? Nice. You submit your work later if you need, if you haven't already. 2x cubed. What's the coefficient in that monomial? 2. Okay. Here's a monomial that has two different powers of variables. What's the coefficient of 3x squared y to the fourth? 3. And what's the coefficient of this last one? Square root of 2. Okay. All right, so those are monomials. The rest of the period, I just want to spend reviewing some rules of exponents. That's it, okay? And then, oh, that's just for me. You'll see why. Yeah. So rules of exponents, we're going to use these a lot from this point on in the class. Most of these are going to be review. Maybe all of them will be review, but you need to get a little practice with these before we jump into polynomials. So first one, the product rule for exponents. This is easy. We've talked about this before. If I multiply like bases, what do I do to the exponents? You add them, sure. So for example, x cubed times x squared is x to the fifth. I add the exponents because I'm multiplying the like base x in this case. Make sense? Okay. Sometimes that gets confused with the power rule, which tells us if you take a power to a power, like a to the m to the n, what do you do to the exponents when you take a power to a power? You multiply the exponents. So for example, x cubed squared is x to the sixth. Okay? All right, so what about the quotient rule? Now let's focus on the blue one for just a second. So you've heard this one before. You've told me this one before. If you divide like bases, what do you do to the exponents? You subtract them, right? So for example, x to the eighth divided by x cubed is x to the fifth, right? 8 minus 3 is 5. Okay, let's jump down for a second to the negative exponent rule. A to the negative m, if I have a negative exponent, that's equivalent to 1 over a to the positive m. So for example, x to the negative 4 is the same thing as 1 over x to the positive 4. Okay, now hold that thought. Let's back up to the quotient rule again for a second, and let's look at what happens if, when we're dividing like bases, the bottom exponent is bigger than the top. So what if I have x to the fourth divided by x to the seventh? What does the quotient rule for exponents tell us? Okay, so I'd get x to what power? To the negative 3, right? 4 minus 7. And what's x to the negative 3 equal to? 1 over x cubed, okay? So what I propose here is that we kind of rethink the way we do the quotient rule, because almost always we want to write our expressions in terms of positive exponents when we're simplifying expressions involving exponents, right? So why don't we do this? Why don't we say that when we're dividing like bases, we're always just going to keep the base where it has the most power, meaning top or bottom of the fraction. We'll keep it where the exponent is biggest and subtract the other exponent, right? And then we can eliminate a step in the process. So for example, when I have x to the fourth over x to the seventh, well, the base has more power in the denominator, and so I'll keep the base there and subtract the 4 from the 7 in the bottom. See how that works? So that's really, I think that kind of becomes your new quotient rule. When you're dividing like bases, you just keep the base where the exponent is biggest and subtract the other exponent, okay? That way you always end up with a positive exponent in your answer. Okay, give me thumbs on that. Does that make sense? Okay, question? Right, so like if we look at these two examples again, x to the eighth divided by x cubed. Where does the exponent, hey, show me thumbs, top or bottom of the fraction. Where does the exponent have the most power? Top, so we leave it there and we subtract 3 from 8. Second example, x to the fourth over x to the seventh. Where does the x have the most power? Bottom, so we leave it there and subtract 4 from 7 on the bottom. See what I'm saying? Okay. All right, so along those lines, we can kind of rethink what the negative exponent rule says also, because it's usually just written the blue way, right? But really, there's two ways it could be. If we have 1 over a to the negative m, that's a to the positive m on the top. So if we always think about the expression as being a fraction, like if I want to create a fraction out of something, I can always just divide it by 1, can't I? Right? Okay, so what this is saying then is if we combine these two into kind of a new and improved version of the negative exponent rule, it would just say this. A negative exponent in one part of a fraction, by part I mean top or bottom, a negative exponent in one part of the fraction is equivalent to or equal to a positive exponent in the other part of the fraction, right? So if I have x to the negative fourth over 1, right, and x to the negative fourth in the top would equal a positive x to the fourth in the bottom. See what I'm saying? Right? So we would send that to the bottom, which just leaves us with a 1 holding the place in the top, right? A negative exponent in the bottom becomes a positive exponent in the top. Do I need to write that divided by 1? No, I don't need to, but that's how I remember that that's really in the top of a fraction. Okay, does that make sense, what I just said? Okay. So those kind of go together, don't they? And then finally, the zero exponent rule just says that any base to the 0 power is equal to 1. There's one exception. What's the one exception, do you think? Yeah, 0. I can't take 0 to the 0. That's called an indeterminate form, and we won't deal with that until you're in my calculus class in a couple of years, and then we'll tackle that one. But any other base other than 0 taken to the 0 is always equal to 1. Okay, so even if it is a really complicated looking base like this one, if I have the base is the quantity 2x cubed y to the 9th, if I take that to the 0 power, it's just equal to 1, because anything to the 0 power is 1. Okay, so then quick reminder, when we're adding or subtracting monomials, of course we can only add or subtract like terms. It's always that way. It was that way with square roots, right? We could only add or subtract like radicals. Those were no, this is some stuff that I just added. You can write it on your paper. Okay, so if we're adding up these three terms here, call this the first, second, and third term. Which of those could I combine? First and the third, right? Okay, good. So it looked like that, wouldn't it? The first and the third are like terms, so they can be combined. And the middle one is a non-like term. That's a different type of term. So that's on its own. It just gets left on its own, right? Separate from the other two. Now, when I have stuff like this, remember that the number out in front is a coefficient. All a coefficient does is count the number of that type of term. So this is telling us I have 7 of the terms of the type x squared y. If I subtract 2 of the terms type x squared y, how many of those do I have? Well, I have 5 of them. Notice that the type of term stays the same though, right? It's like saying 7 apples minus 2 apples is 5 apples. It's not just 5, it's 5 apples, right? The type of thing stays the same. Coefficients are just counting how many of those, okay? All right, and then I'm going to add a couple other rules that don't show up on the standard packet. The power of a product rule and the power of a quotient rule. Okay, so the power of a product rule is this one. It's the one that says if I have a product to a power, I can split that up into the product of the separate powers. In other words, why don't we click them all closed? I feel like I don't have everybody's undivided attention here. Effectively, what it means is when I'm multiplying stuff inside a quantity, I can distribute any exponents, right? So this would turn into a to the m times b to the m. So for example, if I took the quantity 2x cubed, I would have to cube the 2 and get 8, and then cube the x and get x cubed. So I end up with 8x cubed. Okay, and that same thing works for quotients, right? If I have a quotient that's all taken to a power, I can distribute the exponent to the top and the bottom of the quotient, right? So for example, if I have something like the quantity 2 over x to the fourth, well, I'm going to get 2 to the fourth on the top, which is 16, and x to the fourth on the bottom, okay? Now, this comes with a big caution. Don't go too far with this and try to generalize, or you're likely to make a mistake, especially if you try to generalize these bottom two to addition and subtraction. It does not work that way. A plus b, the quantity a plus b to the m is not equal to a to the m plus b to the m. You cannot distribute the exponent when things are being added or subtracted, only when they're being multiplied or divided. That's it. As soon as you add addition or subtraction inside the quantity that's being taken to a power, you can no longer distribute the exponent. You're stuck, okay? Think about what this would actually mean. The quantity a plus b to the m, that would be like saying a plus b times a plus b times a plus b times a plus b, m times. I'd have to multiply m of those together, right? That could be an enormous mess when all is said and done, right? I mean, I'd have to do a whole bunch of distributing. It's just going to get, I'm going to turn into some big, ugly expression. It's much, much more difficult to do something like this than it is if it's just a simple product or a quotient to a power. We're going to spend almost a whole day talking about how we do stuff like this. If we have addition or subtraction involved and we want to take something to a power, that's much more difficult, okay? All right, so then all I really want to do is I want to go through some examples and just practice this stuff a little bit, and then I'll turn you loose and you can start on the assignment. So we're going to look at numbers 2, 3, and 5 on your packet, and then I've got one other one that's not on your packet I want to look at. So there's number 2. Now on all these, we're simplifying, and so we're using regular order of operations. So am I climbing down the PEMDAS ladder or up the PEMDAS ladder if I'm simplifying? Down. Yeah, I'm just going like that, right? Regular, start with parentheses, then exponents, etc. So what would I do first here in this one if I'm trying to simplify? Yeah, inside the parentheses, there's nothing to do. So the first thing would be exponents, wouldn't it? Right, so very first we would do distribute the 2 to all the...
So you do it 3 times because it's negative 2? Oh, because there's 3 different. I thought negative 2a cubed is one term.
No, well, no, those are factors, right? The things that are multiplied are factors. There are 3 factors inside the parentheses, negative 2 times a cubed times b. 3 things are being multiplied, right? Okay, we're going to distribute the 2 to all that stuff. By the 2, I mean the power 2. Get the exponent 2 gets distributed. So what is negative 2 squared? What's negative 2 squared? Positive 4, okay. What is a cubed squared? Yeah, a cubed squared is a to the 6th, and then I'm going to get a b squared, right? Everybody agree? There's step 1. Okay, now I've got to multiply that by 8ab to the 9th. So what's my next step? PEMDAS. What's the next PEMDAS step?
Do you
Multiply. Yeah, that's it, right? So we're going to multiply, right? Now, when we multiply stuff, let's count the number of things that are being multiplied here. 4 times a to the 6th times b squared times 8 times a times b to the 9th. 6 things are being multiplied. So let's be smart about this. How do we want to structure this product?
do it like 4 times 8?
Yeah. Okay, exactly. We do it that way, right? Multiplication is commutative and associative. Commutative means I can rearrange the order in which I'm multiplying stuff. It doesn't matter, right? A times B is the same as B times A, right? Associative means I can group, I always multiply in pairs, and I can group those pairs any way I want to, right? So why not group the pairs and rearrange this at the same time? So we've got 4 times 8 times, I could do the A's then, right? Group those together, times A to the 6th times A times the B's. B squared times B to the 9th. And what's that going to give us? 32. A to the 7th, B to the 11th. Okay, do I really have to write that step out, do you think? No. I mean, I could just do that in my head. Just do the organization in your head. I'm going to multiply the numbers first. Then I'm going to multiply the A's together, the powers with base A. Then I'm going to multiply the powers with base B. Okay? No big deal, right? How about this one? Okay, what's first? Divide. Yeah, we're going to divide. That's step one. Okay, I'm going to divide, and then what's going to be second? Subtraction. But I'll only be able to subtract these if what happens? What do we call those? If they're like terms, yeah, good. So if the variables are exactly the same, if I get pieces of the type m to the 4th n cubed, only if I have the same profile, exactly the same types of variables, can I subtract them. All right, so let's divide first. Well, we're going to use a similar strategy probably, right? How am I going to divide those out? Okay, there you go. Good. So we could do 54 divided by 3 is going to give us 18. And then what? Okay, so m to the 6th divided by m squared is m to the 4th. And then finally, yeah, n to the 4th divided by n is n cubed minus 10 m to the 4th n cubed. So can I subtract those? Yeah, I can, right? They're like terms. So what do I end up with? Good. And that's like saying 18 oranges minus 10 oranges equals 8 oranges, right? The type of thing doesn't change, just the number of that thing changes when I subtract terms. Okay. All right, what about this one? What am I going to do first here? Okay, good. So first I've got to do the exponent in this case, right? Then I'll multiply, okay? So if we distribute, let's see what happens there. If I distribute the 2, I'm going to distribute it to the whole 2/3. What's that going to give me? 4/9. I've got to square the top and the bottom, right? So I get 4/9. Okay. Hey, let's get all earbuds away too. I don't want earbuds that's a distraction. So what about the next part? If I distribute the exponent to the r squared, what am I going to get? What do I get? R to the 4th. And if I distribute to the s to the 7th, what am I going to get? s to the 14th. Okay, times this stuff, right? Okay, so how am I going to multiply these?
Would we cross multiply the fractions?
You don't cross multiply. How do you multiply fractions?
Common denominator.
Straight across, right? We don't have to get a common denominator or anything like that. Multiplying fractions is easy. You multiply straight across. So what's that going to give me when I multiply the fractions together?
4/54.
Yeah, 4/54. Okay. Whoops. Okay, how about when I multiply the powers with base r? Okay, good. So r to the 7th. And then finally, if I multiply the powers with base s, okay, and what's the last thing I could do to simplify that?
If you divide it by 27.
Yeah, good. I could divide top and bottom each by 2 and get 2/27th, r to the 7th, s to the 15th. Okay, good. That all makes sense? Okay. Okay, last one. Now, what about this guy? So there's a little trick here I want to kind of show you. You guys can we'll prove it. What if I have a fraction like a over b to a negative power to the negative m? Okay, I could distribute that exponent to both parts, right? So I'd get a to the negative m divided by b to the negative m. Okay, but what's the meaning of negative exponents? A to the negative m on top becomes, okay, becomes an a to the positive m on the bottom, right? Agreed? Okay, and a b to the negative m on the bottom becomes, okay, b to the positive m on top. And I could undistribute that exponent from both parts of that fraction if I want to, and write that as b divided by a to the positive m. So what's the moral of the story there? What was I able to do? Ah, okay, yeah, a fraction to a negative power is equal to its reciprocal to a positive power. That's kind of nice, right? So we could take this guy here and we could rewrite this as the reciprocal 4x cubed y squared divided by 6x y to the 5th to the positive 2. Okay, good. All right, now we're going to want to follow that. That helps, right? The negative exponent made things a little bit trickier, but now it's just a regular old positive exponent. So if we simplify, what am I going to do first here? Okay, do I want to distribute the power right away? Okay, and how come? Because the first step is parentheses, right? Well, there are some parentheses here that actually, if we look inside the parentheses, there is some stuff to do this time. In the past, there wasn't anything to do inside the parentheses. It was already simplified, but not this time. This time, there's quite a bit I could do inside those parentheses, right? Okay, so what could I do? Well, 4/6 simplifies to what? Okay, so there's one thing I was able to do. That helps a little bit. How about this? X cubed over x becomes x squared where? On the top. Okay, so 2x squared, and y squared over y to the 5th becomes y cubed in the bottom. We'll follow our rule. We keep the y on the bottom because the exponent's bigger, and we subtract 2 from 5 and get y cubed, right? Okay.
He's confused why you put it on.
Okay, because
Why is it not negative?
well, it is, but that's how I tweaked that rule for you guys. Remember, we said we're going to do this a little better way. We're going to say for the quotient rule, we're going to keep the exponent where it has we're going to keep the base where it has the biggest exponent and subtract the other one. And then we don't have to do that additional step of moving the negative exponent to the bottom, right? So here, if we have x to the fourth over x to the 7, we just keep the x in the bottom and subtract the top from the bottom and get an x cubed on the bottom. Okay, it just saves us a step. Okay, and really, if you think about what's going on there, it makes more sense to do it this way. Here, I'll show you an example. Like, let's look at these two examples. Like, if we have x to the 8th over x cubed, x to the 8th over x cubed, isn't that equal to x to the 8th is just this? Isn't that the same as x times x times x times x x times x times x times x, right? X cubed is just x times x times x. Well, look what we're doing here. We're just canceling out 3 of those x's, leaving us with an x to the 5th on the top, right? Everybody see that? Okay. Well, what's going on with this guy here? With this guy here, right? With this guy here, I'm just going to draw a little arrow. X to the 4th over x to the 7th, that's x times x times x times x over x times x times x times x times x times x times x. Okay, look what happens. I'm canceling out 4 of those, leaving me with an x cubed on the bottom. So doing it my way really is what you're actually doing when you cancel those like factors. Okay, does that make sense? Okay. So what's the last thing to do here? Yeah, now we just distribute the exponent, right? So if we do that, if we distribute this 2, oops, that was kind of cool. That's not what I meant to do. What's that going to give us? 4/9 x to y to the 6th. And we got it. Good? Okay, does that work? Okay, how about it? Good. Hmm. Uh,